All right. So we're going to look today at the next lesson in your unit handout. This is on page 7 of your unit handout, and it deals with the period of an oscillating spring. This is all leading up, everybody, to wave motion eventually, and we will deal with that starting next week. We started off when we talked about simple harmonic oscillation a couple days ago, learning that there are two types of simple harmonic oscillators that we study in detail in this course. And one of them is a pendulum, and one of them is the mass on a spring. When we were doing all of this work yesterday, we were dealing with masses on horizontal springs. Today we're going to be dealing with vertical springs. Well, we're going to be doing a little demonstration with vertical springs, and we'll be able to apply what we learned today to vertical springs and horizontal. But what we did yesterday cannot be applied to vertical. Okay? So we're simply going to solve some problems using the period of a mass oscillating on a spring. There's a formula here, and it probably should not come as a big surprise to you that if I have a mass on a spring and I set it into oscillation, it probably shouldn't come as a big surprise to you that the time it takes for that mass to move, I just want to straighten this out. I don't want a spring and a pendulum happening at the same time, okay? And there's going to be a lot of rotation here because the string I have is braided, so it's going to try to unwind. And I don't want it doing that too much, so I'll kind of settle it down a bit. But it probably shouldn't come as a big surprise to you that the time it takes for the mass to go from the bottom back to the bottom is connected in some way to the mass and the spring. I mean, I think that would make sense. Just as a very, what's the word I'm looking for, qualitative approach, if I put this 200-gram mass on this spring, the period is quite small, right? If I put a 1 kilogram mass on the spring, the period is longer. Yes? So if I change the mass, the period changes. So the period is related to the mass. Similarly, though, the period is also related to the spring itself. So if I take a different spring, and I think you realize that the spring constant here is less, right? Very little force to pull at a meter. And if I use a 200-gram mass, and there's no way I'm going to put a 1 kilogram mass on here. If I put a 200-gram mass on here, and I just even use my memory of what the period was like on that other spring, the period on the other spring with 200 grams was less than a second easily. And this is 1/1000. It's more than a second, considerably more than a second, and considerably more than the other period. So it turns out, and we don't get into, nor do we want to get into or need to get into, why this is the formula. The formula is the period of a mass oscillating on a spring happens to be equal to 2 times pi multiplied by the square root of the mass divided by the spring constant. And we have to use standard units here. You have to use kilograms, you have to use newtons per meter, and all of that. What we are doing today is we're going to spend, I'm guessing it's going to be about 15 to 20 minutes going through some examples. Then we're going to do a group kind of demonstration with some calculations to test a few things. And then you're going to have some practice problems. Okay? So it's not a jam-packed lesson. I'm not going to be standing here for the next hour. All right. So determine the frequency of vibration of a 500-gram mass on a spring if the spring constant is 28 newtons per meter. Well, the frequency of an oscillation is equal to the reciprocal of the period. So if we are asked to determine, sorry, get some errant hairs in my face. If we are asked to determine the frequency, then we should be saying, let's determine the period and then take the reciprocal of it. I wouldn't, everybody, take this formula. I mean, some of you might be clever enough to do this and work with it. I wouldn't take this formula and flip it over to find the frequency. You certainly could. Okay? And maybe I'll show that to you in a minute, but I wouldn't do it that way. I would just calculate the period, and then whatever I get, take the reciprocal. So this is a fairly basic question, really. It's 2 pi times the square root of the mass, which is 0.5 kilograms, over 28 newtons per meter. And I'm going to take this opportunity in this to give us a little more practice with units and explain, bless you. Did you sneeze that notebook right off the desk? No. I'm going to take the opportunity to give us more practice with these units. But let's do the calculation first. It's 2 pi times the square root. You certainly don't need to enter times in your calculator. I didn't. You could if you wanted to. Of 0.5 divided by 28. You don't need to close the brackets, but you can. So the period is a little less than a second, about 0.839, well, about 0.84 seconds. And that means that the frequency will be equal to the reciprocal of that. I'm going to write 0.84, but of course, I'm going to use all of my units or all of my decimals. 1 divided by the answer gives me about 1.2 seconds. Not 1.2 seconds, 1.2 hertz. About 1.2 back and forths, oscillations, cycles, whatever you want to call it, per second. Now again, I want to take the opportunity, and this is just to give us practice, because I want you, when you get to Physics 30, for those of you moving on, to be more familiar with unit analysis. Our units, well, let me write this out. Period equals 2 pi root m over k. So what are the units? The units of t will be equal to the units of all this stuff. Well, what are the units of the number 2? 2 is a unitless quantity. It's a number. It's the same with pi. Pi doesn't have any units because pi is a ratio of circumference of a circle to diameter. Whatever the circumference is divided by the diameter, you get the units canceling. But we do have units of this stuff. So the units of m over k will be the units of kilograms over newtons per meter. And I know you're in an advantage if you take Math 20 right now, but there's a really important thing about this line. You never want to write, this is called a complex fraction, you would never write this. Because it becomes ambiguous. You don't know. Something funny? No? Okay. If there is, let me know. I could use a laugh. Because we don't know if this means kilograms per newton over meters, which it doesn't, or whether it means kilograms over newtons per meter. And there's a difference. Okay? So where do we go from here? Well, we want to break down a newton. How many of you know that a newton is a kilogram times a meter per second squared? I would probably say if you do, it's probably not because you've memorized that, it's because you know force equals mass times acceleration. Would you agree? So the units of force, which are newtons, equals the units of mass, which is kilograms, times the units of acceleration, which is meters per second squared. So I'm going to put this set of units right where that newton is, and I end up with the square root of kilograms over, it's going to be really messy. In fact, you know what? Let's get rid of a little bit of the messiness here by multiplying the top and the bottom of this fraction by meters. It becomes the square root of kilograms times meters over newtons. How many of you would just see that, because if you multiply by the reciprocal, the meters goes up top? Okay. At higher levels in math, we tend not to use that rule. We use other strategies. But this is now kilograms times meters over a newton, which is a kilogram times a meter over a second squared. Well, I'm going to multiply top and bottom of this fraction by seconds squared. This cancels, this cancels, this cancels, and you're left with the square root of seconds squared, which is seconds. So it works. All right, let's take a look at number 2. The period of a mass, it happens to be a 500-gram mass again. Can you double check the numbers, that they're the same on your handout? Okay, they are. Is 0.42 seconds. What's the value of the spring constant? Well, all we're going to do is put the numbers into our formula. This time we're going to put the 0.42 here, and I put the units in the previous question because I wanted to have a discussion about units. Let's just leave the units out for this question. Then we have 2 pi and the square root of the mass, which is 0.5 over k. Those of you in Math 20, you have a slight advantage here because this is a radical equation. It contains radicals. And you've been kind of taught that what you want to do is isolate the radical and then square both sides. But even if you haven't taken Math 20, I think it's reasonable for you to understand that if you do that, if I divide 0.42 by 2 pi, I'm left with this. So how would I get inside of that square root, which we call a radical in math? How would I get inside of there? I would square both sides. And we haven't really worked with a formula like this before. You have a number of options. I suppose what you could do is just leave everything together here. You don't have to calculate what this is. I'm going to square both sides here. And what I'm going to have is whatever 0.42 over 2 pi squared is equal to 0.5 over k. I think if you're going to do it this way, now would be the time to calculate that number. I really do. Because if you want to start rearranging this and writing, it turns out it would be k equals 0.5 over that thing, that's awkward. So you can certainly do these calculations along the way. The first thing you need to do is take 0.42 and divide by 2 pi. And of course, if you enter what I've just entered, you will not be on the right track. Because that is not dividing by 2 pi, that's dividing by 2 and then multiplying by pi. You either need to have the 2 pi in a set of brackets or do what I do, which is say, look at the top of the screen here. I need to take 0.42 and I need to do 2 things to it. I need to divide by 2 to get rid of the 2, and I need to divide by pi to get rid of the pi. That's just how my brain operates. Divided by 2, divided by pi. We get the same answer. Now I want to square that number. So what we are getting is this number, 0.004468. Don't worry about the units here. We've had our daily discussion of units. We're done with units for the day. This is equal to 0.5 over k. I really hope at this level everybody knows that k will be 0.5 divided by this number. Right? Whether you just see it or you cross multiply and divide, that's how we're going to get k. So I need to take 0.5, which is the mass, divided by the answer. So it's about 112 newtons per meter. Now, before we move on and finish up with the examples, from the very beginning when we started working with formulas in this course, I kind of explained that there are two ways to work with formulas. One is to put the numbers in and then calculate, rearrange with the numbers in it. The other is to rearrange the formula with variables and then put the numbers in. And we've encountered situations where putting the numbers in first is a better approach. It's not a better approach here. If you take this formula and you square both sides, and let's face it, the problematic aspect of this formula is that square root. That's what the stumbling block is. So if we get rid of it right out of the gate, this is what we get. So I've squared the t, it's t squared. I've squared the 2, which gives me 4. I've squared the pi, which gives me pi squared. And I've squared the square root, which just eliminates the square root, so I'm left with m divided by k. When I said to you, everybody should be able to rearrange this to get to there, the same thing is true here. You should be able to rearrange and get k equals 4 pi squared m over t squared. Lot simpler. Well, I think. You're going to get k equals 4 pi squared m over t squared. Was t 0.46 seconds? 0.42. 0.42, and the mass was 0.5? Okay. Thank you. So 4 pi squared times 0.5 kilograms divided by 0.42 squared. And I just think it's so much simpler, streamlined. I don't know what the word is. But you need the math, right? You can't look at this and go, I'm a little scared of that thing. You need to be able to work with this formula. Any questions with example 2? All right, final example. What is the period of oscillation of a mass spring system that is oscillating with an amplitude of 12.25 centimeters if the maximum speed of the mass is 5.13 meters per second? And you're given the spring constant. So if you start at the beginning and it says, well, what is the period? Then you use this formula, period equals 2 pi root m over k. With a little bit of thought and careful reading, you realize that you're missing the mass. We don't have the mass. But we do know that mechanical energy is conserved well, I mean, geez, I think sometimes we need to say there's no friction, and sometimes it's obvious that there can't be friction, because if there was, we would have no way of solving it. Any type of simple harmonic motion or oscillator that we deal with in high school physics is frictionless. So mechanical energy is conserved. That means that the mechanical energy at x equals a and the mechanical energy at x equals 0 must be the same. And at x equals 0, it's moving as fast as possible. So it's only going to be 1/2 mv squared here, where v is the maximum speed. And at x equals a, it stops for an instant in time, and this is where all of the mechanical energy is potential instead of kinetic, and these two are equal. So it's like there was a problem we did yesterday, and I can't remember which one it was, but Hunter, you had asked about it, right? Question 8, and it was 8b, right? So you needed to find, I think, the speed of the mass at a particular displacement, but we didn't know the mass, but you did know the maximum amplitude and the maximum speed, so you could do yesterday with question 8 what we were about to do here with this one. It's just, you know, we don't learn stuff in isolation. You don't just learn this and then apply it. You still have to be able to apply previous ideas. So what are my numbers here? Okay, so I have 1/2 times the spring constant. I'm sorry, I don't think I ever really said. We need to find the mass from this. That's what we're doing. So that we can put the mass into our period formula and calculate the period. The spring constant is 5.03. I think I saw 12.25 centimeters as the displacement. Don't forget to square it. Equals 1/2 times the mass times the speed. The maximum speed is 5.13. Does that really say meters per second? Okay. The 1/2s cancel. And what I would like everybody to do is calculate the mass. That's quite an enormous speed for something that is only being displaced 12 centimeters from the equilibrium position. I think some of you know what's going to happen here in terms of our final answer. You know what the final answer is going to be like. So the 1/2s are gone. I have to take 5.03 times that 0.1225 squared and divide by 5.13 squared. So I'm getting a very tiny mass, 3 grams. Are you in agreement that that's the same? Did I?
5.03.
Is it 5.03?
Yes.
Okay, thank you. Oh, I see what gotcha. I got you. I'm with you. I missed a 0 here. So this is 5.03. So what I have written on the board is correct. My fingers are just fumbling around on the calculator. And this is 5.13. Is that right? Wow, I didn't even notice those numbers were so close together. They are. Okay. About 2.8 grams, is that what we're getting? So it's a very tiny mass reaching an incredibly large, like 5 meters per second. That if you ran at 5 meters per second, it's not impossible. We can all run at 5 meters per second, but you're really running quite fast. You're not an Olympic sprinter, but you're moving, okay? So this is the mass. And now we can throw that mass in up here, and I really feel as though I don't even want to write the numbers down. Let's just do this on our calculator. I think that's a reasonable request for us. So I need to take 2 pi times the square root of the mass divided by the spring constant, which was 5.103. Okay, which is 5.03. So 0.15 seconds. And how many of you suspected that the period would be very tiny? I mean, it's moving quite fast. So that's the answer, 0.15 seconds. That means its frequency is pretty close to 6 hertz. If I take the reciprocal of this to get the frequency, it's closer to 7 hertz. This thing is bounding back and forth over a total distance of about 24 centimeters, because it goes 12.5, 12.25, 12.25. It's bounding back and forth over this distance, 6 to 7 times per second, reaching a speed in the middle of over 5 meters per second. It's a blur. Any questions with example 3? Okay, so we're going to do a quick kind of demonstration, and we'll do some calculations together. I have 2 springs we're going to do this with. We have the, I will just say we have the spring with a tiny spring constant, and we have the spring with a larger spring constant. And they were the springs we were looking at a little while ago. This spring has a tiny spring constant. And what we're going to do is we're going to calculate the spring constant using Hooke's law. There isn't either, right? You read my mind. Hooke's law. And we're going to calculate the spring constant for each of these using this. And I think we're going to do this with 2 data points. So I have already measured the length of this spring that's hanging from the ceiling from the top of this ring, where the top of the spring starts, to the bottom of this hook. So whatever distance I measure, I'm going to be doing a Hooke's law calculation, which means the force equals kx, or k equals the force over x. Whatever I measure when I put a mass on here, so I'm going to put a 200-gram mass on, and then I'm going to measure the length of the spring. So this is the lab you did, basically. I'm going to measure the length of the spring, and it's going to be spinning like crazy, but that's okay, from the top of this ring to the bottom of that hook. But that's not x. X will be that distance I measure minus the 14.5. So let's see what I get. And look, we're not, if I wanted really accurate things, maybe I could have you hold this and I could take a picture and then we could look at the picture. We're not, splitting the atom here. It doesn't have to be perfect. I am going to say it is 52.8 centimeters. But that means that this x, and this is just my scrap work. You have lots of places where you can write stuff down. This x is going to be, what did I just say, 52.8? 52.8 minus the 14.5. Which is 38.3. Okay. So again, we're not doing a formal kind of lab here. We're just kind of in teaching and learning mode. This is a displacement of the mass away from the equilibrium position. And the force, I actually have a sticker on here. It says 2 newtons. It's not exactly 2 newtons. That's just for demonstration purposes. This is a 200-gram mass. So if we take 200 grams in kilograms and multiply by 9.81, this is the lab you did. That will be the force. So for one data point for this spring, if we take 0.2 times 9.81 and we divide by 0.383 meters, the value of K I'm getting for this spring using Hooke's law is about 5.1 newtons per meter. And it's interesting that as we've been talking, the mass is now in oscillations for some reason. And it says it's swinging back and forth as a pendulum and it's bouncing up and down as a mass on a spring. So I'm going to say 5.1. And let's quickly run through another one. I'm going to double that mass and use 400 grams. And I think I can get away with 400 grams here without ruining the spring. This is going to require a little more ingenuity to measure that displacement. But I'm going to ask Georgia, I don't know if you have really good eyes or not, to do your best, and I'll do my best to hold this steady. We're looking for the measurement to the bottom of that hook. Sorry, I can't hold it more steady.
89.3.
Wow, good eyes. 89.3. So we would have to take the 89.3 and subtract the 14.5. This is the displacement in centimeters. So now I'm going to take 0.4 kilograms, because it's 400 grams on there, times 9.81 and divide by 0.748. And as far as a lab goes that's just kind of off the cuff without any real rigid controls. That's pretty good. We're getting 5.1 newtons per meter, and we got 5.2 newtons per meter. Well, let's do this now using our formula, and I'm going to go with 200 first. Using our formula, if I can get this thing off of here, there it is, for the period of the mass on a spring. And why don't we rearrange that first? We actually have it rearranged here. We can save us all a little bit of time. Right? 4 pi squared m over t squared. Now, so you're going to, by the way, I replaced all the batteries in our stopwatches, but I don't think we need to hand them out. Let's get some phones out. And from what I recall here with this particular mass is with 200 grams, when I get it oscillating, it's going to take a very short period of time for it to start swinging around. So I'm going to ask that we measure the period for, or the time for 5 complete oscillations. So as a practice run, this is what's happening. We're going to start, say, here, 1, 2, 3, 4, 5, and end there. And you can already see it starting to drift back and forth. So we want to know a period, and we're not going to average everybody's data, but I'll ask a few people for the results. You're going to start your stopwatch at the bottom, and you start it at the bottom whenever you want, and you're going to count from there, 1, 2, you're going to stop at 5, okay? I won't tell you what I have. Christina, what do you have?
I calculated too early, but I have 6.18.
That's, oh, I have 6.25. So 6.18, 6.25. Have you got one?
Yeah, 5.07.
5.07? No? Didn't bother? I didn't, that came out, that didn't come out right. I didn't mean that. I didn't mean there's something wrong over there. I just meant you didn't do it. That's fine. Have you got one?
5.84.
5.84. Ethan?
6.37.
Okay. Shannon, have you got one? No? I think we'll go with the experts over here and say, let's go with 6.2. I got 6.25. Christina got 6.18. Anybody else get right around 6 point something? Yeah. I'll tell you why I'm going to go with that, because I did this morning before class started, and I actually got pretty much the same answer, and I tried a few trials. So that's 6.2 seconds, we'll say, but that's for 5. That's for 5 complete oscillations. So we need to divide 6.2 by 5, and by my count, we get 1.54.
2.24.
2.0.
1.24.
1.24, thank you. 1.24. So we're going to put that here. The mass is 0.2 kilograms. So it's 4 times pi squared times the 0.2 kilograms divided by 1.24 squared. I mean, it doesn't get any better than that. In terms of comparable results, you know, the average of Hooke's law, and I don't want to eat up too much of your time because we do have some problems to work on. We won't repeat it with 400 grams. You're going to be doing a lab, by the way, involving this. The analysis will be different, but we got 5.14. The average of these two is 5.15. I admit I'm kind of, picking and choosing how to analyze the data, but they're pretty close, aren't they? Let's do quickly, we'll just do one set of data, but we'll use the other spring. So we'll do a Hooke's law calculation. And the length of this spring is 24 centimeters from top of hook to bottom of hook, or top of ring to bottom of ring, or whatever you want to call those things. And let's go 1 kilogram. So I'm going to first of all do the Hooke's law. You know, I almost want to go 1.5 kilograms. Okay, so I'm going to need your help again. And I hope it's not more than a meter. No, it's not more than a meter. So again, we're going from, I guess we want centimeters, not inches. I'm just going to try to stop it from spinning.
71.6.
71.6. So with Hooke's law, with 1.5 kilograms, it's 71.6 is the length, but we have to subtract 24. So 71.6, and those, I'm sure you see that. The lengths of the springs are written on the sideboard, okay? Minus the 24, you know, we have to divide by 100 to get, we have to divide by 100 to get it into meters. So this is the distance, the displacement. I need to take 1.5 kilograms and divide by that. It's about 3 newtons per meter. Are you getting the same answer? That doesn't seem right to me.
Don't you have to multiply by 9.1?
Yeah. It seemed way too small. Thank you. Yes, I have to multiply by 9.81. This is only the mass, not the force. So now I divide by 0.476. That seems more reasonable. 31 newtons per meter. So now what we're going to do, and you know what? Let's just use a different mass to calculate the period with the other formula. It doesn't have to be this mass, right? We're just using a different type of analysis. Let's use 1 kilogram. And the reason why is I think more of you will be able to see the mass. At 1.5, it's not almost at the floor, but it's pretty close. We'll do the same thing. I think we can do, let's just do a trial run here. I think we can do 10. I don't think this one bounces around. No, we better go 5. It does start to sway. By the way, it doesn't matter, and this will be something you learn in the lab you do, whether I do this or do this. Because the formula says the period only depends on the mass and the spring constant, not the amplitude, which is interesting. So as I've been talking, it's been bouncing up and down, and it hasn't really changed direction. So let's go with 5, though. Now, I'm right here, so it's easy for me to watch it. And by the way, if you got a time that was significantly lower last time, remember when it reaches the bottom for the first time, that's not one cycle. You go start, then 1, then 2, etc. But I'll let you guys off the hook here and just tell you what I got. I got 5.7 seconds for 5 oscillations.
5.77.
5.77. Faye? 5.7. Let's call it 5.7. Divided by 5 gives 1.14. Yes? So the period is 1.14 seconds. We got 31 newtons per meter as a result from Hooke's law out of this formula. And by the way, for our first spring, didn't we get 5.1 newtons per meter basically as well? Okay. Out of the formula here, what are we going to get? I said 1.14. I'll show you the formula again at the top of the screen. It's 4 times pi squared times the mass. I have 1 kilogram on there, divided by the period squared. again, you know, it doesn't, as far as experimental results go, this is why I like stuff with springs and pendulums and, you know, projectile motion. You're not trying to measure some weird time. It's easy to measure. It's not a kinematics thing where you have to find the speed of an object. They're accessible measurements that are very easy to get good values of, and you get good results. So we got 31, and this rounds to 30. That's pretty good. Maybe if we did it for 10 oscillations, it might be more accurate. But there's got to be human error there. When you take a look at the Flying Pig Lab, many of you got well, some of you didn't get that close to the acceleration due to gravity, but there are sources of error. But it's easy if you're careful with that lab to get a very accurate value for the acceleration due to gravity. Some of you had a problem because your pig was it was a special pig. It was kind of flying around in a weird way, had some difficulty, it was uncoordinated. We will do a lab next week with a pendulum where you should be able to, if you're very careful, get within 1 or 2% of the acceleration due to gravity just by timing a pendulum going back and forth.